Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we are going to show, mathematically speaking, a very useful result. First, let me write it down for you. Okay. It says the following. Let y be a discrete random variable with mean, and I'm going to be using that Greek m, mu, to denote the mean of y, and variance, and I'm going to be using a Greek s, a sigma, square to denote the variance of y. Okay. Now, if a and b are constants, we want to show that this result has two parts. Part 1, we want to show that the expected value of a times y plus b equals a times expected value of y plus b. That's the first part of this result. The other one has to do with the variance. Now we want the variance of a times y plus b. And it turns out that the variance of a times y plus b equals a square times the variance of y. And if we use the sigma notation, right, what we have is a square times sigma square. This is just notation, right? Okay, here goes our proof. Proof. First, number 1, part 1. Okay, so we're going to start from the left hand side of this equation, and we'll see if we can reach the conclusion. So first, note that this is the expected value of a sum, and as we said in another video, the expected value of a sum equals the sum of expected values, right? And we know this by a particular theorem. In your textbook, this theorem is theorem 3.5. That's the label that they used for it. Okay? But again, this is what I want you to remember. The expected value of a sum equals the sum of expected values. Okay, let's keep going. Now, the expected value of a times y, given that a is a constant, we know that we can factor out that a, that constant. This is the same as a times expected value of y. Okay? And again, in another video, we proved that result. Okay. And if I remember correctly, in your textbook, this the expected value of a constant times a random variable being equal to a constant times the expected value of the random variable, they labeled it as theorem 3.4. Okay, let's continue. Note that b is a constant, right? And something else that we showed, another useful result regarding expected values, is that the expected value of a constant is the constant itself. So this turns into this again, because the expected value of b, because b is a constant, is b itself. Okay? And that's by another useful theorem that we have already shown in another video, and this one was labeled in your textbook as theorem 3.3. Okay? So as you can see, we started from the left hand side of this identity and we reached the right hand side using results that we have shown previously. Okay, so we're done with part 1. Let's show part 2. It's similar, but in that case we want the variance. Okay, let's try and do the same. So first let me label this a times y plus b. Let me relabel that as a random variable w. Okay? Just a label, but it's going to help us. Now, the expected value of w is going to be what? Is going to be a times the expected value of y plus b, and that's by, you know, what we just did, right? Expected value of w is going to be this. Make sense? Now, let me use the mu notation, mu, and a subscript, so we know that we are referring to this new random variable, w, which is equal to a times y plus b. So this is the mean of w. Okay? Okay. Now, here we go. So, finding the variance of a times y plus b is the same as finding the variance of w, right? But by definition, right? By definition, the variance of a random variable w is just expected value of w minus its mean the whole thing squared. You guys agree? That's just the definition of variance. Now let me expand what we have here. Okay, let me use curly brackets here to make it more readable. So w is the same as a times y plus b, right? So wherever I see a w, I'm going to just replace with a y plus b, right? Minus. Now we know that the expected value of w, mu of w, is given by this. And that we have from the first part that we showed. So anyway, we're just substituting the value of w and the value of the expected value of w. Now note something interesting here. If we expand this, and let me do that, here what we're going to have is ay minus a times expected value of y. Okay, so let me just rewrite this. Instead of having just this here, I'm going to place it here. So that's what we have. ay minus a expected value of y. Okay, I'm just multiplying by that -1. Now this guy is going to be minus b, right? And we have a b here. Can you see what we're doing here? So a times y minus a times expected value of y, right? These two terms, this one is that positive b that we had, and then this is minus times b minus b, so these two guys will cancel out. Okay, so now the only thing that we have left is these two terms, a times y minus a times expected value of y. But note that something that we can do is this is a common factor. So let's factor it out. This is the same, and let me here close that curly bracket, right? Okay, so anyway, we could factor out that a here, can you see that? A times y, this guy, a times expected value of y, right? Okay, now that square is affecting a, and that difference, the difference between y and its expected value, that happens to be just the following. As you can see, this is going to be the same as a square times y square. You guys agree? What we have is a times y minus expected value of y, the whole thing square. So this is going to be a square times the square of that difference, y minus the expected value of y. Right? Now, what we have is expected value of a constant times this. We know that we get to factor out that constant, right? That's one of our theorems, right? So let me rewrite this as just the a square times the expected value of y minus its expected value, the whole thing square, right? And we did that by one of our theorems, right? I think that the one that would be relevant here is theorem 3.4, that the expected value of a constant times a random variable equals a constant times the expected value of the random variable. Okay? Okay. So, finally, note that the expected value of y minus its expected value, the whole thing square, that is just the variance of y by definition. So this is the same as a square times the variance of y. Again, this is just the definition of variance. And if you prefer the other notation, the sigma square notation, then this is the same as a square times sigma square. Okay, so as you can see, we have shown our result. Okay, let's summarize. What you have to remember again is that if you have a mathematician friend, what he or she will tell you is this: if you have an original random variable and you create a linear combination like this, a times y plus b, it turns out that the expected value of a times y plus b equals a times the expected value of y plus b. That means that the expected value is linear. Okay? Now, here, what you have to remember in this case is that the variance of a constant is 0. Okay, that's really important. Another thing that you have to bear in mind is that the variance of a constant times a random variable is not, I repeat, a times the variance of y. It is, what it is a square times variance of y. Okay? You have to square that constant if you want to factor it out. Okay? Well, thank you so much for watching. Please take care and keep working hard. See you next time. Bye.